Well, good evening, ladies and gentlemen. It's a great privilege and pleasure to welcome you all here today, especially those who are visiting Gresham College for the very first time. And I'd like to extend a very, very special welcome to our speaker today, Professor Tim Gowers of Trinity College, Cambridge, Rouse Ball Professor of Mathematics, and probably known to you best as a winner of the Fields Medal in Mathematics. These are awarded every 4 years for exceptional performance in mathematics. It's very, very rare for anyone to get one, and we are delighted that Tim Gowers, who won the Fields Medal in 1998, is speaking to us today. So I'll hand over to Tim, who's talking about multiplying and dividing whole numbers.
Thank you very much. One of the sort of occupational hazards of being a mathematician is that you occasionally have to talk to non-mathematicians who have very little idea about what it is that mathematicians do. And there are various questions that come up, of which two are relevant to what I'm going to talk about today. One is, how can there be such a thing as research in mathematics? People sort of, when they're at school, their experience is that maths is just sort of handed down to you from on high, and that's what there is, and how could you then sort of discover more maths? Surely that's what there was, the stuff that you learnt at school, and it's difficult to see how you could develop more of that thing. And then some people make a bit more of an effort and then think, well, is it, you know, sort of just multiplying larger and larger numbers together or something like that? And so you then have to take a deep breath and say, well, no, it's not quite like that. So I want to give some idea of what research in maths is like. So I've decided to talk about multiplying larger and larger numbers together. But there's a slight twist, of course, which is that the focus is not so much on sort of let's take some really super big numbers and spend the next hour multiplying them together. It's more like the general question of how to go about it. But in order to think about that, and by the, then later on, there was division in the title as well. So later on I shall talk about the sort of companion question. If you've got a number that's a product of two other numbers multiplied together, how can you find those two numbers? So how can you factorize? And that's another school topic. You're given a number and you're asked to factorize it. But again, it's a topic that gets a bit more complicated if the numbers get bigger. And there are good reasons for being interested in that question, which I'll come to later on. But just to get warmed up, let's actually do a bit of multiplication. And just to prove that I haven't sort of cheated, I'm going to ask for somebody in the audience, anybody who feels like it, to suggest to me a 4-digit number, and then someone else to suggest another 4-digit number, and we'll multiply them together and just remind ourselves how the process works. Yes? 5079. Yep. Was there another volunteer over there? Yes. Times 3636. Right.
Is it in decimal?
Oh, yes. So, I'm curious, actually, probably looking around, I should think the average age in this audience is such that most people here probably did, at some stage in their lives, learn how to do long multiplication before the age of calculators and so on. But younger people in the audience, I'm just curious to know, actually, do they teach long multiplication in schools, or is it just a ridiculous thing because when you've got two numbers like that, you can you just plug them in your calculator? At school, you just plug them in the calculator, or would you know in principle how to multiply them together if you just had a... You would? Okay, so I'm very glad to hear that it's still being taught. Another theme of... so let's just quickly do it then. So what do? You take, let's take 9 times 3636, and then we'll do 7 times 3636, and then we'll do 0 times 3636, and 5 times 3636.
That's the other way, isn't it? Because if you do it the other way, then root them up with 3, then you've just got double that, and you shift it twice, and there you are.
I just want to do it, what do you mean, because the 3, yes, okay. Actually, for that very reason, let's take a more general number. So it's a slight... I'm making life harder for myself rather than easier, okay? So let's have a 36 something else. 94, okay. So we're not going to do it the other way, just because we're not going to have any sort of special properties. All right, so 5079 times 3694. So let's do 9 times 3694. So 9 4s are 36, so I carry a 3, 9 9s are 81, so that's 84. Carry 8, 9 6s is 54, so that's 62. 9 3s are 27, 33. If anyone spots me making a mistake, please shout. 7 4s, if I put a 0 there, 7 4s 28, 7 9s 63, so that's 65. 7 6s are 42, plus 6 is 48. 7 3s 21, plus a 4 is 25. Now I can do a nice easy one. Put 2 noughts, and then some more noughts. And then 5, 3, 6, 9, 4. Well, I could sort of divide it by 2 or something instead. But let's just do it first of all, 3 noughts. Right, 5 4s are 20. 5 9s are 45, plus a 2 is 7. 5 6s are 30, plus the 4 is 34. 5 3s are 15, plus the 3 is 18. And then we have a nice last stage where we add all this stuff together. 6, 4 and 8, 12. 2 and 5 is 7 plus 1. 3 and 8 is 11. 3 and 5, that's 8 plus 7, 15. And I carried a 1, so it's 16, 7. 1876, 1826. I was slightly surprised that it came out with that nice form. Now, I'm going to get rid of this calculation in a minute, but I want the answer. So let's just write it slightly smaller up here. 1876, 1826. Actually, I sort of think the talk should perhaps have been given a different title, which is why it's easier than you think. Because actually what I'm going to focus on to start with is better methods that take less long of multiplying numbers together. But the sense in which it's more difficult is that there's more to say about the whole question of multiplying large numbers than you might think. So the sort of general theory of it is more complicated than you just do long multiplication. So that's the sense in which it's going to be a little bit harder. Now, there's a nice trick. Actually, before we go on to the nice trick, let's just think about what we were doing here and why it works. This is something that may be taught a little bit less at schools, but not at all, I hope. I hope that was deliberate 2 knots there. I hope it is taught somewhat. But let's just think a little bit about why this method works, because that will help later on. So the idea is that 5079 we think of as 5,000 plus 0, which I perhaps better not worry about here. In a way, I was also tempted to cheat and change that 0 into something else just to be a bit more general, but let's not worry about that. So plus 70 plus 9 times 3694. And in order to work that out, you say, well, it's 9 times 3694 plus 70 times 3694 plus 5,000 times 3694, and then you use the rule that if, say, you want to work out 70 times 3694, you work out 7 times 3694 and stick a 0 on the end. And so that's what we did. We had the 3 numbers, 9 times 3694, and then 70, or 7 times 3694 shifted by 1 with a 0 on the end, and 5 times 3694 shifted with 3 noughts on the end. And so that's basically why the method works. So we reduce the calculation to multiplying this number by single-digit numbers over here and then putting noughts on the end. And then there's a bit of addition at the end, but addition is somehow easy and a relief after you've done the multiplication. So that stage we don't worry about so much. Now, for the purposes of... So I'm beginning to regret more and more that wasn't more than a 0, but I think I'll press on with the numbers that I was given. It was 3694, so let's split that up as well in the same way, and then I can illustrate a different method that's also quite nice. So now I've split up both numbers, and a different way of organizing what is basically the same calculation, but it's a better way of organizing it, is to say, well, if you want to multiply these things together, then you've got to do 5,000 times this, and 5,000 times this, and 5,000 times this, and 5,000 times this, and 70 times this, and 70 times this, and 70 times this, and 70 times this, and 9 times this, and 9 times this, and 9 times this, and 9 times this. Now, one idea that you can do when you do that process is to think, let's collect together all the various sums that are going to have a particular number of zeros on at the end. I'll do that very systematically. How can I multiply one of these numbers by one of these numbers and not get a single zero on the end? It's going to have to be just a 9 times a 4 because everything else involves 0. So I got the 9 times 4 term, which gives me 36. Now, how many things are going to end up with 1 0 on the end? Well, there'll be 70 times 4 and 9 times 90. Well, let's not worry about the 70. Let's think of it as 7 and a 9 here, and then put a 0 on at the end. So I put a 0 on. Now I've got 7 4s, that's 28, plus 9 9s is 81, and 81 plus 28 is 109. So I'll put 109 there. That's the sort of 1 0 contribution. How do I get 2 zeros? Well, if there were a hundreds term here, there would be 3 ways. I'd have the 100 thing times a 4, a 70 times a 90, and a 9 times 600. As it happens, we're sort of lucky, so to speak, that there isn't a hundreds term there. So we've just got 2 ways of getting 2 zeros, and they are 9 times 600 and 90 times 70. So for getting the 2 zeros part, you get 54, that's 9 times 6, 54 plus 63, and 54 plus 63 is 114, no, 117. So I've got 2 zeros and a 117. So that's 2 zeros. How do I get 3 zeros? Well, I can get it with 5 times 4. Let's write something down now, just to be a little. That's 5 times 4. 1 0 here would have to go with 2 zeros, which it can't. 2 zeros with 1 0, so 6 times 7, that's a 42. And finally 9 times 3, which is 27. And so that's 89. Nearly there. And 4 zeros. How do I get 4 zeros? I've got to have 1 with 3, that's 45, or 3 with 1, that's a 21. 45 plus 21 is 66. 5 zeros can only happen if I've got 5,000 times 6,000, so that's sort of 600, so that's 30 plus 5 zeros, by which I really mean 30 times 5 zeros. Well, 30 times 1 plus And last of all, how do I get 6 zeros? I have to do 5,000 times 3,000. So I get 15 with 6 zeros on the end. So let's put that 15, 0, 0, 0, 0, 0, 0. Well, I was instructed not to write too far down on the whiteboard. I'm sorry about that. But the calculation just sort of pulled me down there. But most of the time I will try to avoid that. So let's now add all this stuff together. And let's write the answer up here. So I've got a 6 there. And an advantage of doing it this way, you'll notice there are an awful lot of zeros here. The numbers that come up, if one thinks about it, tend not to be all that big, and so the addition part is actually easier than the addition part in the other method. So we get 6, and then we get 3 plus 9 is 12, carry 1, 7, that's 8, 1 plus 1 plus 9 is 11, so that's a 1, carry 1, so it's 2, 3 plus 9 is 12, 2 plus 8 is 10, plus 6 is 16, 6 gives you 7, 1, 8, 7, 6. What's that 2 doing there? That's very curious. How many digits? 1, 2, 3, 4, 5, 6, 7, 8. And I've got a 9-digit number there, so I must have done something very, very stupid. Everyone? I must have done something stupid round about here. So 1 plus 1, that's 11. And, oh yes, let's just cross that out. So 11, 1 plus 1 is 10, 18, 26. I just sort of wrote a 2 for no reason at all, I think. Anyway, it's quite reassuring-ish that we've got the same number that we had before. After a little fudge factor, we've got the same number that we had by the previous method. Now, I've got a transparency. Let's see whether I'm ready to put it up, or whether I need to discuss a few more things. So what I want to talk about now is... Actually, no, I'm not ready to do it, because I now want to talk about a method of multiplying two numbers that is a lot faster than this if the numbers are huge. If the numbers are too small, like 4 digits, then just the sort of brain ache you get from thinking about the method is not worth it. You might as well just do it the stupid way. It takes slightly longer, but at least you didn't have to use your brain. But if you've got two numbers that are 1,000 digits long or something, and you can save 25% on the time that it takes, or in fact a lot more, but even a small saving on the time is really worth it, especially if, as sometimes happens, you are running a computer program for which it's important to be able to multiply large numbers together quickly. First, I should say, while I'm just getting rid of this stuff here, that underlying a reason for being interested, one reason that is a good reason for being interested in quite a lot of what I'm talking about, is so-called public key cryptography, which is the method that is used these days for doing things like encrypting your credit card details so that somebody else can't steal them. And that involves a certain amount of number theory, the branch of maths that is involved with sort of things like prime numbers and factorizing and that kind of thing. And in order to get this system to work, you will be dealing with large numbers, and you'll need to be able to multiply them together in a hurry and that sort of thing. So any speeding up of your basic method of multiplying large numbers converts into a much quicker way of encrypting your credit card details. And a small saving in time, if you're a company that's sort of encrypting millions of credit card details every day or something, it really makes a huge difference. So this is not just a sort of surprising, nice little fact that you can actually do it more quickly. I'm actually going to talk about a method that really is used in real life, and it's rather important. So let's imagine ourselves with two absolutely huge numbers. So we've got two numbers, 2,000-digit numbers. And let's just give ourselves a crude idea of roughly how many little operations that we'll need to do, little operations, i.e. multiplying one-digit numbers or adding one-digit numbers, we will need to do if we want to multiply two 1,000-digit numbers together. Well, at the very least, if you think about the first method, let's just imagine we've got number 1 laid out like that and number 2 laid out like that. What happened with the first method? Well, we took the last digit of this number and multiplied it by this. So if this had 1,000 digits, we had to do about 1,000 steps as we went through multiplying by a one-digit number. So we had about 1,000 steps, and then we dealt with the last digit of this number. Another 1,000 steps, and we dealt with the second last digit of this number. Another 1,000. So we get 1,000 times 1,000. So ordinary long multiplication takes round about 1,000,000 steps. Well, it's not much fun doing 1,000,000 calculations of that kind. So it would be quite nice if we could find a quicker way. What about the second method? Does that actually help us? Well, with the second method, we still had to compare every single digit of this number with every single digit of this number. We collected them together in a clever way, but we nevertheless had to do one multiplication for every digit you could choose here and every digit you could choose here. And there are 1,000 ways of choosing a digit here, 1,000 ways of choosing a digit here, so at least 1,000 times 1,000 operations are necessary. So again, you need at least 1,000,000 operations. I'm not saying precisely what I mean by an operation, but I hope you get some sort of idea that the number of steps is around 1,000,000 if you use either of those two methods. So now you might think, well, what else could you do? And this is an example of what makes mathematical research so interesting. You look at a problem like that and you think, surely there isn't anything else you could do, and then you discover that somebody's actually come up somewhere in the world with an incredibly clever method that actually improves on this 1,000,000. But there are varying degrees of cleverness that you can go in for, and one of the simpler ones is simple enough to explain to, I think, an audience like this. I don't know what your backgrounds are, but probably varying quite a lot. But I think if you've done a bit of long multiplication, I hope you'll be able to follow what I'm going to say next. So the idea is to use what's called, what mathematicians like to call a divide and conquer strategy. So here's what we'll do. I'll draw a different picture of the two numbers. We've got 1,000-digit number here, and I'm just going to split it up into its first 500 digits, which I'll call a number A, so that's a 500-digit number, and it's sort of followed by its next 500-digit number, and I'll just designate that by B. So B represents the last 500 digits, and A represents what happens if you subtract B and divide by 10 to the 500. And then the other number, we just sort of think of as C times, or not C times D, but C times 1 followed by lots of noughts plus D. So there are two numbers, and we'll do a sort of long multiplication type process to this lot of four numbers. So let's first of all look at the contribution that has no zeros on the end. That'll be B times D. So I got a BD here. Let's write B times D. And now I'm going to have a contribution that's got 500 zeros on the end. And that'll be the A followed by 500 zeros times the D, or else the B times the C followed by 500 zeros. And if I multiply those numbers together, I'll get so A times D plus B times C followed by 500 noughts. And then the third thing I'll do is something which is followed by 1,000 noughts. That's if I multiply the A part and the C part. So A with lots of noughts and C with lots of noughts gives me A times C followed by 1,000 noughts. And then we will just add these numbers together. We'll add B times D, which is a number that's one 500-digit number times another 500-digit number. And we'll have AD plus BC, that's some 500-digit numbers multiplied together with 500 noughts on the end, and A times C with 1,000 noughts on the end. So this is rather like long multiplication, except that instead of splitting the numbers into 1,000 little blocks of one digit each, I'm just splitting them into two blocks of 500 digits each. But it's the same sort of idea behind the procedure for multiplying them together. So what this has told us so far is that if I can work out A times C, A times D, B times C, and B times D, then we'll be in good shape. Now, to multiply 2,000-digit numbers together, it took roughly the square of this number operations. I had one digit from each number, so it took about 1,000,000, which was 1,000 squared. And the same argument works for 500. So if I want to work out B times D, it's going to be about 500 times 500 operations. And 500 times 500 is 250,000. So it'll take me 250,000 operations to work out B times D, 250,000 operations to work out A times D, 250,000 operations to work out B times C, 250,000 operations to work out A times C. Total, 250,000 times 4 equals 1,000,000. So now, most people would look at that and think, well, that was a nice idea, but it doesn't get us anywhere, and go off and have a cup of tea or something. But mathematicians have this stupid habit of thinking, well, do I really have to give up at this point? Let's just have a look at this thing. I really don't need to work out all four numbers, A times C, B times D, A times D, and B times C. What I really need is A times C, B times D, and those two added together. I don't care what these two numbers were themselves, I just need to know what they are added together. And then the following bright idea can occur to one. So I'm going to go to a bit more algebraic and use the notation BD for B times D, because it makes things a little bit more convenient. So I've got four numbers, A, B, C, and D, and I want to know the numbers AC, AD plus BC, and BD. And I like adding and subtracting, because compared with multiplication, they're much, much easier. And I really hate multiplying. I want to do as few multiplications as possible. So the obvious way of doing it will involve 4 different multiplications and 1 addition. So can we do better than that? And the answer is yes. So let's get rid of this now. Of course the answer is yes, or I wouldn't have gone on like this. But, all right, so how do we do it? Well, what we do is there's a little trick. which is we work out what is A plus B times C plus D. Now, before I go any further, just notice, to work out A plus B, you just have to do an addition. An addition is sort of cheap, easy operation. Same with C plus D. Now, A and B have, sorry, that should be, that's all right. A and B have 500 digits each. So how many digits has A plus B got? Either 500 or 501. So not much larger than A itself. So we don't have to worry that this number has suddenly become much, much bigger or anything like that. It's got roughly the same number of digits as A and B themselves. So this is a nice, easy multiplication to do. And what does it tell us? A little bit of algebra here, which, incidentally, is just the same as long multiplication in a sense. We work out A times C, then A times D, and B times C, and B times D. So we get AC plus AD plus BC plus BD. So with just one multiplication, we've got that. Now, this was the thing we didn't want to do, so let's just forget that one for a moment. That's what we'd like to know, AD plus BC, but we haven't actually. Supposing instead we just do three multiplications. We do A times C, B times D, and A plus B times C plus D. Well, once we do that, if we subtract the AC and the BD from this answer, what do we get? AD plus BC, which is precisely the third number that we wanted to calculate. So how many multiplications have we done? Just three. A times C, B times D, and A plus B times C plus D, and then a little bit of addition and subtraction afterwards. So how many operations did that take us? Well, each one was 250,000, because these are about 500-digit numbers. So the total is not 4 times 250,000, but 3 times 250,000, which equals 750,000. So instead of 1 million operations, we managed with 750,000 operations. Now, of course, at this point, I think even a non-mathematician will think, well, perhaps we shouldn't stop there. We had a little clever idea for multiplying large numbers together. Can anyone see what to do? Well, I expect a few people can. We just do it again. When we work out A times C and B times D, and A plus B times C plus D, don't do it by long multiplication and take 250,000 operations. Do it by this clever method. And instead of taking 200, well, basically, each time you apply the clever method, you save yourself 25% on the time that you took before. So you save yourself 25%, but for goodness sake, when you're doing when you're doing these calculations, save 25% on those as well. And then your total saving is 25% followed by another 25%, which gives you 3/4 times 3/4, which equals 9/16. And 9/16 is not much over a half. So now, if we apply this clever idea twice, we actually have now taken only half the amount of time that we would have taken before. But of course, we don't have to stop there. We've got 250-digit numbers, so we can do it more and more times. And just to give a rough estimate, let's see, how many times can we keep dividing the length of our numbers by 2? Well, if they started off as 1,000-digit numbers, that's about 2 to the 10. So maybe about 10 times you can halve the length of your numbers. And each time you do it twice, you sort of roughly halve the length of the calculation. So you can halve the length of the calculation about 5 times. I'm being slightly generous to myself here. But so you can divide the length of the calculation by about 32, which takes you from 1 million down to more like 30,000, or let's say 40,000, because I was a bit, I cheated slightly in my very rough estimates. Now, you have to agree, even if 750,000 isn't much better than 1 million, 40,000 really is going to take your computer a lot less time than 1 million. And it turns out that that's not the end of the story. Now, let me just see I'm about halfway through my time. So I think that gives me time to discuss a little bit more of an advanced idea. I'm not going to discuss it in an advanced way at all, but there is an idea that leads to a saving that's so good that multiplying two very large numbers, say 2 n-digit numbers, is almost like multiplying 1 n-digit number by just one very small number. So in the case of 2,000-digit numbers, it's sort of like reducing the problem to something about as difficult as multiplying a 1,000-digit number by, say, a 6-digit number or something like that, which is a really remarkable saving on what you would do if you just applied ordinary long multiplication. And it's just the sort of thing that until you've seen how it's done, you would think could not be possible, but it is. So I'm going to discuss a concept that's very important in many parts of mathematics called convolutions. It's a rather alarming word, perhaps, but the concept is not very difficult, and it's connected with how you multiply polynomials together. And that's very much what we were doing when we did the second method of long multiplication. So if you don't like x's, imagine that this x is 10, and this a and b are some numbers. If you want to multiply, in fact, let me just remind you what the idea is that I'm talking about and that this will be generalizing. So if I wanted to multiply 35 by 46, I would take the 3 times the 4 and put 2 noughts, because that's 10 squared, and then the 3 times 6 and the 5 times 4 would be just a 10 to the 1, which would be a sort of x, and the 5 times 6 would give me a 30 with nothing on the end. Similarly, in general, when you multiply ax plus b times cx plus d, and you collect according to the power of x, so an x squared comes from the a and the c, so we get a times c times x squared. The x comes from the a times a d and a b times a c, that's this ad plus bc, and the constant term, or the x to the naught term, which equals 1, is just the b times a d, and you get a bd. I'm going to just generalize this more and more. So what happens if we have, this is something that maybe if you haven't done it a few times, you think, I don't want to do that one. Ax squared plus bx plus c times ex squared plus dx plus f. But once you've done one of these, you suddenly get the general pattern, and that's what I want to get across. So the general pattern here is very similar to what we had with the second method of long multiplication. We have a sort of power of x to the 4, which can only come from an x squared and an x squared. So we have a times e, and that's what I've written here. The x cubed can come from pairing this term with this term, or this term with this term. So that gives me AD plus BE, and there's my x cubed. And then the x squared term comes from A with F, B with D, or C with E. There it is down there. And the x term comes from either B with F or C with D, and the x to the naught term is just C times F. So I think you can see the general pattern emerging. You have the two brackets, you fix the power you want, and you sort of do that term with that term, 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 that term, until you've sort of reached the end of one of your brackets, and then you've got the relevant term. The problem that arises a lot in mathematics is getting notation for things. How are we going to notate what happens in general? It's fine with this, fine with x squared, and with x cubed I could have a plus b plus c plus ax cubed plus, I could use a, b, c, d and e, f, g, h in the other bracket. After a while I start to run out of letters. And what if I want to talk about a general polynomial that might have degree n for some positive number n, and I'm not telling you what the n is? How do I notate that? Well, eventually you just have to give up. And you can't use letters of the alphabet anymore, or you can't use n different letters of the alphabet, especially if you don't know what n is. So you just have one name, but you put a little number by it. So the coefficients, as they're called, the numbers that were a, b, c, and d are now called an minus 1, all the way down to a1, a0, and bn minus 1, down to b0. And you have to think of those as just any old numbers that you put in front of x to the n minus 1. Because we've run out of names, we have to have this system for naming them. And then what's the coefficient of x to the 2n? Well, that can only come by pairing an with bn, so we get an with bn. And then you get an with bn minus 1 and an minus 1 with bn. And again, I hope you can sort of see the pattern emerging. Each time I go along one of these rows, this number goes from n minus 1, n minus 2, and then the other one goes upwards, n minus 2, n minus 1, n. And similarly here, this goes n minus 1, n minus 2, n minus 3, and this one goes up from n minus 3, n minus 2, n minus 1 up to n. The middle term starts with an and b0, and then an minus 1 and b1. You go all the way down, you get to a1, bn minus 1, a0, bn, etc., right down to the last one. That's not quite the last one. The last one slipped off the bottom. There, the very last one is a0, b0. Can that be seen? Yes, there it is. a0, b0. Now, even if you didn't follow the justification for that, just take it from me that here are 2n minus 1, I think, different numbers, And if you can work out all these numbers, then you can work out the product of this expression with this expression. And if x is 10, then these could represent just numbers that you want to multiply together. And the process that takes the sequence of numbers a0 to an and b0 to bn to this bunch of numbers is called convolution. And it just comes up all the time because multiplying polynomials comes up a lot of the time as well. So the general message is, again, the details are not so important. The general message is there's a thing called convolution. It's what you do when you do long multiplication by the second method. If you know how to do convolutions quickly, you know how to do multiplication quickly. But the trouble with convolution is that, as you have just seen, it's a little bit of a complicated operation. You've got these sort of funny numbers that you're taking this times this, plus this times this, plus this times this, plus this times this, and it's all a bit of a complicated, not very pleasant looking thing. Wouldn't it be nice if instead we did something called pointwise multiplication, where if you had your two sequences, you just took a0 times the corresponding b0 and a1 times the corresponding b1. If you did that, then you could make the mistake that many, many generations of school children have made, and multiply 3x plus 5 times 2x plus 7. Well, we multiply the 3 by the 2, and we get 6x, and the 5 by the 7, we get 35, and so that's the answer. And I think it's the sort of thing my children would say, and then they say not at the end. It's a generational thing. Or an alternative would be to be really ingenious and say 6x squared plus 35. So we multiply the 3x by the 2x and get 6x squared, and the 5 by the 7 and get 35. And never stop to think, well, if we'd swapped the 2x with the 7, would we then have multiplied the 3x by the 7 and the 5 by, and things like that? Those sorts of questions don't occur to everybody, unfortunately. But nevertheless, we have this, so let's get back to that. We have this sort of lament that convolution was a rather horrible, complicated thing, whereas pointwise, or point-by-point multiplication is a lovely, easy thing to do. And it's a terrible shame that when you're multiplying numbers, you have to do this convolution thing instead of pointwise multiplication. Now, this is where a piece of mathematical magic comes into play. Something called Fourier transforms. Fourier transforms have the wonderful property that they turn convolutions into pointwise multiplication. So just to say a little bit more about what that means, there's something called the Fourier transform. That's the bit that I'm really not going to explain. But it takes a sequence of numbers, and you put it into a sort of little machine, it chugs away and produces a new sequence of numbers. And that new sequence of numbers, you traditionally stick a hat on the old sequence of numbers, and that's what you've got when you've done the Fourier transform. Now, the Fourier transform has the wonderful property that, as I've just said, that convolutions turn into pointwise multiplications. Now, what do I mean by that? I mean that this diagram, well, try and stop myself from saying this diagram commutes, but that is what I really want to say for professional mathematicians. But what it means is, if I do a convolution of two original sequences, and I look at what happens to their Fourier transforms, I find that their Fourier transforms just do a pointwise multiplication. Or to put it another way, if I take my two original sequences, I have two choices about what I could do. Either I can work out their convolution directly, and that was really a horrible, unpleasant thing, or I can put them into the Fourier transform machine and find two new sequences, and in those ones I just have to do a nice, easy pointwise multiplication. And then they have to sort of go backwards through the machine, and when you put them back, you'll get back to your original convolution of your original two sequences. So the pointwise product over here turns into, when you do an inverse, so this machine has the property you can put things in this way, and it turns things into their Fourier transforms, and you can put them in this way, and it takes the Fourier transform and gives you back the original sequence. So it so happens that it's a bit like logs, actually. If you've done logs, there's a sort of logarithm machine. If you don't like multiplying, stick them in a log machine, add, and then push them backwards through the log machine, and you get the product. Fourier transform is like a sort of super sophisticated machine that, instead of turning addition into multiplication or multiplication into addition, turns convolution into this simple pointwise multiplication. So as long as you know how to work out the Fourier transform, then you've got a nice, easy way of convolving. You take the Fourier transform, you do the pointwise product, and you do the inverse Fourier transform. And so that raises one very obvious question. Is the Fourier transform something that's easy to work out? If the Fourier transform is very hard to work out, then this is not going to be an extremely good method for working out convolutions. And then there's another miracle. There's something called the fast Fourier transform. As its name suggests, it is something that can be done rather quickly. And so if you put all those ideas together, the fact that long multiplication really is what it's really asking is that you should be able to do a convolution, and that convolutions are made much easier if you can take Fourier transforms, and that Fourier transforms can be done really surprisingly quickly. You put all that together and use a bit, so that's some quite serious mathematical theory going into that, and it ends up telling you that you can do much, much more quick. You can multiply numbers much, much more quickly than long multiplication. Not just a bit more quickly. This trick certainly saves quite a lot. Using the fast Fourier transform, you could get it down from, so here we got down from 1 million to whatever it was, about 40,000. Using the fast Fourier transform, we might get down to more like 2,000 or 3,000 or something like that. So you get a really huge saving. Now here's an example of a typical open problem in mathematics. I haven't told you enough for you to be able to go away and think about it or anything, but the question is, could we do even better than the fast Fourier transform method? And the answer is nobody knows. And it's one of those things where not only does nobody know a better method, but the answer might be no. There might not be any better method than that, and nobody has the faintest idea how you would show that you can't do better than some method. How would you show that some clever person couldn't come along and do an even better method? And it's very, very, somehow, that belongs to a branch of maths called complexity theory. It's a problem in general of trying to show that certain problems can't be done easily, say by a computer. And the problems of complexity theory really are very, very hard indeed. Right, so I'll switch this off for a bit. And now I'm going to come to the second part where we talk about dividing or factorizing numbers. So that's all I have to say about multiplication. It's harder than you think in that the theory that goes into it is harder than you think, but it's easier than you think in that it doesn't take as long as you think if you use that theory. The fast Fourier transform really has revolutionized a lot of algorithms that are used in the real world. Now, let's take a number like, say, 437, and think about the question whether it's a prime number or not. So I'm going to, this is again a very, very traditional sort of school exercise. What do? We say, well, does 2 go into it? No. Does 3 go into it? Well, let's add the digits. We get 14. 14 is not a multiple of 3, so 3 doesn't go into it. Does 5 go into it? No, because it ends in a 7. Does 7 go into it? No, because if I subtract 7, I get 430, and 7 goes into 420, so it obviously doesn't go into 430. Does 9 go into it? No, because 3 didn't go into it, so we only have to look at prime numbers here. Does 11 go into 437? Well, you may know a little test that if the odd digits add up to the same as the even digits, something like that, 11 doesn't go into it. In fact, 11 goes into 440, so it obviously doesn't go into 437. Does 13 go into it? Well, let's add 13 to this, and we'll get 450. And does 13 go into 450? No, because it's 2 times 5 times 9 times another 5 or something. So 13 doesn't go into it. This is getting slightly dull, but we know that if this is going to be factorizable, we'll have to reach a factor by the time we get to the square root of 437, which is around about 20, because then the number that you're trying to go into it will sort of overtake the number that it would have to multiply by, and so we would have already checked it. So let's just press on a little bit longer. So 13 doesn't, what about 17? Well, if I subtract 17, I get 420, and 17 doesn't go into 420 because that's 10 times 6 times 7. How about 19? Well, 3 9s are 57. If I subtract 57 from 430, I get 380. Does 19 go into 380? Ooh, yes, it does. It's 20 19s. So this is actually 23 times 19. Well, that was a rather... Now, let's just follow the pattern of the first half of the talk. Let's imagine we've got a 1,000-digit number, and we'd like to decide whether that's a prime number. So here it is. And let's try to think how long it might take. Well, if we don't want to keep tabs as we're going along of every single number and whether it's prime or not, which is going to make us take even longer, it's probably better just to see whether 1 goes into it, 2 goes into it, 3 goes into it, 4 goes into it, 5 goes into it, and so on. This had 1,000 digits. So we know that by the time we've tested all the numbers up to 10 to the 500 or so, and whether they go into this number, we'll be all right. Now, it's not much fun testing whether a number goes into a 1,000-digit number when that number itself has something like 500 digits. But let's just be very, very generous to ourselves, and let's suppose that you could do on your cleverly programmed computer, which you certainly couldn't actually, 1,000,000 such tests every second. So 1,000,000 numbers you can test whether they go into this 1,000-digit number every single second. Let's write that 1,000,000 down. And let's be very generous and suppose there are 100 seconds per minute, and 100 minutes per hour, and 100 hours per day, and 1,000 days per year. So that's how many operations you could do every single year. And how many noughts have I got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I've got 10 to the 15. I managed to do 10 to the 15 tests per year. So how many years do I need? Well, if you're on to your, up with your, what 10 to the 500 actually means, you'll find the answer is 10 to the 485 years. And when you've done that, you've worked out whether that number is a prime or not. As you can see, the drawback with that, it really is a terribly bad method to use. And I think this is a case where it's even more remarkable that there are fast ways of deciding whether a number is a prime. And I'm going to give some slight idea of how that's done, and some slight idea. Actually, the other thing about it, if you've got a number that is given to you and it happens to be a product of two very large numbers, can you find what those two large numbers are? That's something where there are methods that are cleverer and quicker than just pure trial and error, but not that much cleverer and quicker. And it's because nobody's found really good methods for that problem. So I'll just say, well, again, what the problem is. It's the problem, you're given a number that's a product of two very large, say, prime numbers, and you have to find what those two prime numbers were. There aren't really good, quick methods for that. If there were, you'd have to start worrying about credit card transactions on the internet. So that's, in a way, it's sort of good news that factorization is hard, but that should raise a little sort of paradoxical thought. I've just told you that it's very hard to decide whether a number has, or to decide what the factors of a number are, but not so hard to decide whether a number is prime. So that must mean, if what I've just said is not rubbish, that sometimes you can tell that a number is not prime, even though you can't say what the factors are. Because if it was easy to say what the factors were, if it's difficult to say what the factors are, but easy to say whether it's got some factors, it must mean that there are ways of saying that a number has some factors without actually telling you what the factors are. That's a remarkable fact. Again, totally unexpected if you're not a research mathematician, where you sort of get used to surprising things happening. And I will give some indication of how that could possibly be the case. It looks as though it can't be the case, but it can. But before that, let's just think a little bit about a very, very quick discussion of factorization. So I've said there aren't any really good methods of factorization, but there are at least some tricks that work sometimes, and here's one of them. Let's take a number 6351. Anybody fancy telling me that's a product of... actually, I wanted a bigger one, actually. Let's not go for 6351. No, I will stick with that. That's fine. So it is fine. Does it divide by 3? What have I done? Oh, yes. Okay. Let's go for another one then. Okay, I'm not going to be defeated by this. So let's go for 8051. So we had a little clue. But I first of all went for 6351, and now I've decided, no, I won't do 6351, I'll do 8051 instead. So that gives a slight clue about how one might go about factorizing this. Well, I haven't got time to wait for somebody to have a brainwave, so I'm going to do something which I really, in a way, hate doing, which is just to sort of leap straight to the answer. Has it got a 17? I don't think it's got a 17, because 17 is going to 50. What happens if you add 1 to 63? You get 64. And if you add 1 to 80, you get 81. What do numbers 64 and 81 have in common? They're squares. So 8051 equals, this is the little trick, 8100 minus 49, and 8100 is a perfect square, and 49 is a perfect square, so we can write this as 90 squared minus 7 squared, and that's 90 plus 7 times 90 minus 7, another thing that I hope everyone under the age of 18 absolutely has at their fingertips. And that's 83 times 97. That was a much better choice, because 83 and 97 are prime numbers, and that's what I meant to do in the first place. But instead I went for 73 times 87, and 87 is divisible by 3, and that was my stupid mistake. So that way, it's rather a nice way, in fact, of coming up with really huge numbers that you can sort of factorize quite quickly. And it also gives an idea of a general method for searching for factors that's a little bit more systematic in a way than just sort of pure trial and error. What you could do is you could say, well, let's just see if I can find some small square that I can add to this to get a big square. And in this case, I thought I could try 1, 8052, is that a square? Not really. What about adding 4, 8055, no. And then I keep going and I get to 49. If I add 49 to this, I get 8100. Oh yes, that's a nice perfect square. Had I had that method in mind, I could have not bored you with the factorization of 437, because if I add 4 to it, I get 441, which is 21 squared. And so this is 21 plus 2 times 21 minus 2, and there it is for you, 21 plus 2 times 21 minus 2. So the problem with this method is there's absolutely no guarantee with the number you started with that when you start adding some small squares, you'll suddenly hit upon a nice big square. Why should that ever happen? Well, actually, it will happen if the number can be factorized. The problem is not whether it'll happen or not. It's just that it might take such a long time to happen that you'd be trying so many things that it wouldn't be any better than the trial and error thing that you were trying to avoid. But all I'll say about this is there's a cleverer method that starts with this basic idea and develops it a bit more. As I said before, mathematicians have this ridiculous thing of just not giving up when they seem to reach the end of the road, just trying to push and push and push and push. And people have pushed and pushed and pushed in this instance and got a method that, if I spent the whole hour, I could have explained that method, but I've got other things that I want to talk about. In fact, in my final 5 minutes, I want to go back to this question that I raised a moment ago of how it could ever be possible to prove that a number was not prime without showing that it was a product of two smaller numbers. So, actually, I didn't need to get rid of that. It's based on something called modular arithmetic, or to give it its more friendly name, clock arithmetic. The clock arithmetic is the sort of arithmetic we all do. If it's 10 o'clock, then what time will it be in 7 hours? It'll be 5 o'clock, because we sort of visualize a clock. We go 2, and that gets you sort of to 0, and then the other 7 hours get you to 5. So every time you pass 12, you're sort of back to 0 again. This isn't a normal clock. This is a clock with 13 hours instead of 12. That's because, for various reasons, prime number clocks are much more useful and significant in mathematics than numbers like 12 that are composite, because they can be built up out of 2s and 3s and things. But just to get the feel of clock arithmetic, let's do some. So what's 3 plus 4? It's 7. What's 9 plus 10? It's 6, of course. And what does that mean? It means if it's 9 o'clock and there are 13 hours in the day, then 10 hours later it'll be 6 o'clock. And 10 hours later it'll be the same as sort of minus 3 hours later, because there are 13 hours in the day. And that's why adding 10 is the same as subtracting 3, and we get to 6. Similarly, 12 plus 3, we can look at the picture for that one. 12 goes to 0, to 1, to 2. The convention is that the largest number is, I mean, in a normal clock, if you were doing it with clock arithmetic, the convention would be instead of writing 12, you'd write 0. Here, instead of writing 13, I've written 0. And you don't just add, you can also multiply. What does 5 times 5 mean? It means, well, I do 5 times. So I go around 5 hours to 5, another 5 hours to 10, another 5 hours to, be very careful, 1, 2, 3, 4, to 2. That can't be right. It is right. 5 hours to 7, and 5 hours to 12, and 5 times 5 is indeed 12. Another way of working out 5 times 5 and getting 12 is to say 5 times 5 is 25, and then when you subtract off 13 from 25, you get 12. So 5 times 5 goes 25, and how do you get to 25? You go once round, and then another 12, and that gets you to that 12. So that's another justification for the statement that 5 times 5 is 12. 7 times 10, well, it starts to get a bit boring to go 7 and another 7 and another 7 and another 7, 10 times. So there it's quicker to say, well, 7 times 10 is 70 in normal arithmetic. In clock arithmetic, what you do is you divide by 13 and take the remainder. And 13's into 70, they go into 65 and leave a remainder of 5. And there we are, 7 times 10 equals 5. That's the remainder when you divide 7 times 10 by 13. And now, my second thing that I just, something that would typically be taught in a first-year course at university, so I'm not going to do anything more than just telling you what it says and illustrating it here so you get some idea of what it means. A thing called Fermat's little theorem, not to be confused with Fermat's last theorem, which is the famous result that was solved a few years ago, but Fermat's little theorem, which is, has been known for centuries. And it says that if you take a prime number clock and raise some non-zero number to a power, you get 1. And just to say what that, let's just illustrate that with a clock of size 5, let's say. So you've got 5 hours a day. Let's take 3. So I'm saying taking p equals 5 and a equals 3. So I've got to work out a to the p minus 1. So that's 3 to the 5 minus 1. That's 3 to the 4. And I've got 5 hours a day. So 3 to the 4 is 81. What's the remainder when you divide 81 by 5? It's 1. And that's exactly what this theorem tells you will always get when you do a comparable calculation. Let's have another example. So the theorem says if you've got any clock with a prime number of hours a day, you use that to form clock arithmetic or modular arithmetic, give it its proper mathematical name. Then you take any number and raise it to a power p minus 1, then you get, you get 1. Let's have a more complicated example. Let's just see what happens if we work out 2, and it's very important that nobody interrupts at this point. We work out 2 raised to the power 90, and I've got a 91-hour clock. Okay, so off we go. We're going to work out the powers of 2. And the rule is that every time I get above 91, I can work out the remainder modulo, or work out the remainder on division by 91. So here are the powers of 2. I'll start with 1. That's 2 to the 0. So I get 2, 4, 8. There are quicker ways of doing this, but actually I think for simplicity I'm just going to do it in a really basic way. So just working them out. No clever methods at all. 64. Now it starts to get slightly more complicated. The next one is not 128. But 128 minus 91, which is 37. Now I'm back to doubling mode. 37 doubled is 74. Doubled is 148. And I've got to subtract 91 again. So that's 148 down to 57. And then I double that. That's 114. Take away 91 is 23, I hope. Just check that one, because it's very important not to make a mistake here. I think that's okay. 46, double 46, I get 92, which, nice, it's 1. If you've ever tried working out powers of 2 and looking at their last digits, just in ordinary base 10 arithmetic, you get 2, 4, 8, 16, 32, 64, 128, 256, and the last digit goes 2, 4, 8, 6, 2, 4, 8, 6. And you can sort of see once you begin to repeat, you must carry on repeating. Once I've got to this 1, it's going to have to keep going through this sequence over and over again. So let's see what that tells us. That's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So when I get to 12, I'm back to where I started, and I want to work out 2 to the 90. So if doing it 12 times gets me back to where I started, then so does doing it 84 times, because 84 is 7 12s. So if I do it 84 times, so I get that 2 to the 84 equals 1 in this funny 91-hour thing. So 2 to the 84 is 1, so 2 to the 85 is 2, 2 to the 86 is 4, 2 to the 87 is 8, 2 to the 88 is 16, 2 to the 89 is 32, 2 to the 90 is 64. And now we sort of think, oh dear, I just told you a little theorem that says that a to the p minus 1 always gives you 1. And now I've taken a as 2, and p is 91. I've worked out 2 to the 91 minus 1, and I haven't got 1. I've got 64. So what's the solution to this little problem? Well, all school children are taught, if you're ever going to use a mathematical fact, make sure you are absolutely certain that all the things that are required by that fact really are true. So what are they? We really have had a number p. We really have had that we've taken a to the p minus 1. The only thing that we haven't checked is that 91 is a prime. Now, is 91 a prime? No, 91 is a carefully chosen number. That's the smallest number that isn't prime, but isn't sort of completely obviously not prime. It's my favorite. So it's 7 times 13. But what you have to notice about this method is that what we've done here is actually establish that 91 is not a prime without actually knowing that it was 7 times 13. It's not a prime because this theorem didn't work. And the theorem always works when it's a prime, and so it's not a prime. And for very big numbers, that is a much better method. Unfortunately, it doesn't always work, but it's another situation like the factorization methods. There's a slight development of this method that does, well, it leads to what's called a random primality test. You sort of try various, you keep on trying various tests, and if your number passes all those tests, then the chances that it's not prime are really incredibly small. So you can be as confident as you like that it's prime, and very, very recently, actually, people have come up with a genuine short method for testing whether numbers are prime. Again, it doesn't tell you what the factors are if it's not prime. But I'm now out of time, but I've just given you at least some glimpse of how sometimes it's possible to prove that numbers are composite without actually factorizing them. And that's it.
As you all know, this lecture is a joint lecture with the London Mathematical Society, and I'd like to hand over to Professor Alice Rogers to say a few words on behalf of the LMS.
Thank you. Well, I'd like to begin by thanking Professor Gowers for an illuminating and a fascinating lecture. I think many of you will, like me, even if you're not a professional mathematician, have thought that you really got multiplying and dividing sorted, and there wasn't much you could learn from a lecture about it. And indeed, I have often told my more tiresome relations that doing more advanced mathematics is not doing bigger and bigger sums. And now I find I was completely wrong. Not only am I completely wrong, but I've discovered this in a most entertaining way and in an extremely lucid and clear way. So let me repeat our thanks to Professor Gowers for the lecture. And I would also like to thank Gresham College for having organised this lecture. And I'd like to say that it's the second in a series of lectures, at least I hope there'll be many more, certainly at least one more is planned, of joint lectures between the London Mathematical Society and Gresham College. And it's a very new tradition, but I hope that it will go on and on because it's quite clear from tonight that it's a very valuable and enjoyable tradition.
So thank you, Tim. This is the last of the mathematics lectures for this year. Next year, we have a lot of things provided for you. I have one more year as Gresham Professor of Geometry, and the first geometry lecture will be on the 3rd of October, when in that one lecture I shall cover 4,000 years of geometry, so get in there early so you can keep up. There will be 3 lectures before Christmas, 3 lectures after Christmas. Also before Christmas, in November, there will be the annual joint lecture with the BSHM, the British Society for the History of Mathematics, and that's being given by June Barrow-Green of the Open University, and she'll be talking about mathematics from the First World War. It's a fascinating talk. I've heard her talk on that before. And Alice said there is another a joint lecture with the London Mathematical Society that will be next. The lectures of the LMS tend to alternate between applied topics and pure topics, and next year we go back to applied mathematics on the 1st of May next year, when Professor Philip Maney of Oxford University will be talking about mathematics and biology, how cancer, how the relationship between cancer and mathematics. So lots of exciting things next year. Looking forward to seeing you then. Thank you very much.